Today, we'll be talking about the Frenet frame. Well, when we deal with normal objects in 3 dimensions, we typically use what we call an orthonormal basis. We have I in the x direction, j in the y, and k in the z. Now, an orthonormal basis is one where every vector has a magnitude of 1 according to the definition of a norm in that basis, and every vector is orthogonal to one another via the inner product. And of course, when we're talking about regular 3 dimensions, orthogonal usually means perpendicular. Okay, so now this is what we're looking at right here. So we have I, j, and k. Each one is perpendicular to one another, and each one has a magnitude of 1. But the Frenet frame is another basis. It's another orthonormal basis. And this one is defined on a curve. So if we have some weird looking parametric curve, like let's say a helix, what do we have? And I'm going to signify it's a helix, just like so. Okay, so this helix is spinning around and spinning around. And so the Frenet frame consists of 3 things. First of all, the tangent vector. Then we have a second vector, which is a little bit harder to define. But essentially, imagine that approximately in this area, our curve falls within a plane. So in this case, I'm going to say our plane is right here. So then we define a normal vector like this. It's actually a unit normal vector, meaning it has to be shortened as well. So this is what we call n of t. And finally, we have the cross product of these two. These two are already made to be perpendicular, so their cross product is just going to be the magnitude of one, which is equal to 1, the magnitude of the other, which is also equal to 1, multiplied by sine theta, which is 90 in this case, which is also equal to 1. Meaning this last vector, the binormal vector, is also going to be a unit vector. Alright, great. So now we have 3 perpendicular vectors. This third one has to be perpendicular to the other 2 because that's what the cross product is for. So now let's look at a few examples of what this is useful for and why. So first of all, how do we calculate each of these? The change in the sky over time. So the tangent vector is just going to be d, let's call our curve gamma, d gamma dt. So this is just the normalized version of that, which is d gamma dt divided by the norm of d gamma dt. Alright, so we can look at an example. If we have a circle over here, you would expect over time that, for example, if at t equals 0, we're right here, the unit tangent should look like this. And it should gradually rotate around. Right? Oh, I shouldn't make that sign. So, you know what we have here? Well, we can start by defining this as, let's actually call it cosine t sine t. So that at t equals 0, it starts here. So then that means that the derivative, which is the tangent vector, is just going to be minus sine cosine. Oh, because it actually goes this way. Great. Okay. So that means that it's actually going to point in this direction, and we're going to start tracing out a circle counterclockwise. All right. So that's the unit tangent. What about the unit normal vector? Well, that's a little bit more complicated. Now, on the face, it's just equal to the normalized version of dt ds, where s is actually arc length. So what does that mean? Well, parametrizing with respect to arc length means that we have a form of the function x of s, y of s, z of s, whatever it is, such that if s is equal to 1, then the total length of the function from s equals 0 to s equals 1 is 1. If s equals some number, then the total length of the function where s equals 0 to that number is going to be s naught. Okay, so this is essentially defining it based on length, which means that if a curve, which is defined by time, starts going fast over here, well, and then it's going to slow down here. So if we have something like this, what's dt ds going to look like? Well, the arc length is going to increase very rapidly as we move over here, and then it's going to slow down when we get to here, and then it's going to speed up again when we get over here. So how's the tangent vector going to change? Well, the tangent vector changes very fast here, and it changes very slowly here, which means that the normal vector is going to be very small. The normal vector is technically not going to be very small, right? But in which way is the tangent vector changing over here? It's kind of changing in this way. Meanwhile, which way is it changing over here with whatever little change it has? It's kind of changing in this way. So that's essentially what the normal vector tells us. And finally, the binormal vector is technically on the surface just a vector constructed specifically to give us an orthonormal basis. But it also kind of tells us if our curve is going out of the plane, which way is it departing? So two very related concepts are curvature and torsion. And torsion in specific is even equal to dn dt dot b. So what does this mean? Well, this is not always going to be equal to a 1, right? Because this is going to be this, which is not necessarily 1, times this, which is actually 1, times theta between them. So this gets a little bit complicated, but this tells you how much it fails to be in a plane. So ideally, if torsion is equal to 0, this should be in a plane. So if torsion is equal to 0, that means that cosine theta is equal to 0. Or in other words, these two vectors are orthogonal. So what would dn dt being orthogonal to b make? Well, think about it. The normal vector, as I said, is kind of defined like we approximate the curve as being planar at a specific point, and then we draw the normal vector to that curve. So if a curve is actually planar, the normal vector isn't going to change because it's always going to be staying within the same plane, which means this is going to be equal to 0. So it doesn't even matter. All right, so that's it.